Alright guys, today we're going to start talking about forces on a ramp. So most likely at this point we haven't really seen any angles appearing in any of our forces problems. This is going to be the first exposure we have to an angle in forces problems. So what we want to take a look at here is just the basics. If you notice, I haven't even put a problem, I haven't even put something specifically to solve for. We're not going to truly solve a problem here. We're not going to solve for acceleration or the friction force or anything like that. I just want to show you the first step in starting to set up a problem where you have forces on a ramp. So that's what we're going to be looking at today, just the first step. What you're going to find is that anytime you have a problem that looks like this, most of the problem-solving process is going to be exactly what we've already been doing. Finding the net force using help minus hinder with a free body diagram, solving using algebra, using the same formulas we've been using. The only trick is going to be this first step that I'm going to show you today. So here's how we handle a problem that looks like this. You can see I drew a basic free body diagram in our simplest example of an object on a ramp. So this object has weight going straight down and it has normal force up at an angle. Please don't forget that. This might be one of the first times that we've actually seen normal force not going straight up. But if you remember the definition of normal force always acts perpendicular to the surface. So we tilted the surface, so we're going to tilt the normal force. So again, weight goes straight down because gravity always goes straight down. We can't change gravity just by putting a box on a ramp. Normal force does go up at an angle. We did change the normal force. And let's put a couple of values in here. Let's just say the mass of the box is 50 kilograms. And let's just say that the angle of the ramp is 30 degrees. Alright, if you guys think back to projectile motion, first thing we need to do anytime we see an angle is we need to split up some vectors. Let me give you an example of what I mean. When you solve this in a projectile motion problem, I hope you remember that the first thing you had to do, the absolute first step, was split this vector up into its x and its y components. We didn't have any formulas that could account for 5 meters per second at 40 degrees. Yeah, sure, that was the initial velocity, but what we need to do is we need to find Vox and Voy. And we use trigonometry to help us find Vox and Voy. So it's going to be the same basic idea over here. We're going to need to split a vector up into x and y components. Well, over here things are going to be a little different. I'm going to follow a specific rule. My rule is the object's acceleration should always be on the x or y axis. Normally, that's what we do just naturally. We've worked with a lot of horizontal forces problems where the box or an object is going horizontally. We've worked with problems like elevator problems where the object is moving vertically. And so the object's acceleration really was on the x or the y axis, just naturally. Here, the box is, in this case, going to slide down the ramp. Notice, by the way, there's no friction. So what we're going to do is, just for forces on a ramp, we're going to tilt our x and our y axis. We're going to make this the y axis. And we're going to make this our x-axis. And so by tilting our x and y axis, what we've done is we've followed this rule. The object's acceleration will now be on the x-axis. Right now we have normal forces on the y-axis. We don't need to split normal force up into its x and y components. mg is going to be the force that we have to split up into x and y components. In the future, you could have applied forces, you could have friction forces, but the nice thing is, usually, those other forces that we can add to these problems to make these problems a little more complex, a little more rigorous, those forces usually will lie on the x or y axis. So what we've done here by tilting the x-y axis is not only follow my rule, the object's acceleration should always be on the x or y axis, but we've also made it so that usually we'll only have one force to split up. So let's talk about splitting this force up. Really, the title of your notes at this point, I don't want to say it before because it wouldn't have made much sense, but what we're learning how to do is split up mg. So just to recap, we have very little given. We're not even solving a problem. What we're doing is splitting mg up into its x and y coordinates. And we're splitting up mg because we have to follow my rule. The object's acceleration should always be on the x or y axis. So we had to tilt our axis. We have this crooked x-axis that's parallel to the ramp, and we have this crooked y-axis that's perpendicular to the ramp. So normal force sits right on the y-axis, but we have to split mg up because mg doesn't sit on the y-axis or on the x-axis. So now we're going to draw a triangle, kind of like usual. Please be careful when you're drawing your triangles. This is the only correct way to draw this triangle. I have MGY right here. And MGY is obviously parallel to my y-axis. That's the only way you can draw MGY. And then perpendicular to MGY is MGX. Sometimes at this point I like to come off to the side and redraw the triangle entirely. So this is MG, always going straight down, and always your hypotenuse. You can even put a little h here next to it. MG is indeed always the hypotenuse. MGY, that's going to be the y component. And again, that should be roughly parallel to your y-axis. It should be exactly parallel, but when you're drawing, I'll take roughly parallel. So that's MGY. And then finally you have MGX. People lots of times struggle to draw this triangle correctly. I've seen a couple of different things. I don't want you to write these wrong examples in your notes unless you really emphasize in your notes that these are wrong examples. I've seen people try to draw triangles that look like this. So some people look at the triangle I drew and they hate it. They can't stand that you have a triangle standing on its tip. I understand it looks a little goofy, it might be a little unconventional or something you haven't seen in math class before, but you can't just redraw it and change the directions of the vectors. These directions matter. MG needs to be going down, and over here MG is not going down. MGY and MGX are not parallel to their corresponding axes. So this triangle is wrong. What's even worse is when people are really determined to try to draw this triangle, but draw it what they call normal looking. Draw it so that it's not standing on its own point. And so I've seen people try and draw a triangle that looks like this. They put MG here, going straight down, like, all right, I'm good. And then they draw MGY parallel to the y-axis. And they say they're happy there, and then they draw MGX. And MGX even looks horizontal, which is normal. The problem is that's also wrong. In fact, this one's way worse. Now MG is not your hypotenuse. Now MGY, well, that one is actually parallel to your y-axis. That's the only one that may almost look correct. MGX is not parallel to your x-axis. And don't forget, y and x, they should be perpendicular. So the right angle should be here, but that's no right angle. Not even close. You form some weird right angle over here where it doesn't belong. So this is also a bad example. If you are saying to yourself, how do I know if I redrew my triangle correctly? Well, I think there are 4 things that should be true about this triangle. If you redrew your triangle as you're trying to separate MG into x and y components, 4 things should be true. Number 1, MG should be straight down. Always, gravity goes straight down. And it should be the hypotenuse. I kind of lump those together as one fact, or one set of facts about MG. MGY should be parallel to your tilted y-axis. So you already have the tilted y-axis over here. MGY should be parallel. MGX should be parallel to your tilted x-axis. And finally, MGY and MGX, they should be perpendicular. There should be a right angle between them. So that's where the right angle should go if you've done things properly. All right, we've drawn our triangle properly, which is getting us a lot closer to our overall goal of this whole video, which is to separate MG into MGY and MGX, we're splitting mg into its components because we have an object on a ramp. So we have our triangle drawn properly. I think I've went over that extensively now. For us to actually be able to do some trig, well, we're going to need a couple of numbers in this triangle. So we're going to need to know the hypotenuse. We know the hypotenuse is mg. I know m is 50. So m times g is going to be 50 times 9.8. So mg, the hypotenuse, is going to equal 490 newtons. So that's mg, 490 newtons. So mg is 490 newtons. Now if you think back to trig and how we're going to be successful solving for mgy and mgx, we don't just need the hypotenuse, we're also going to need an angle. So I have to go back to my original drawing for that. I see this angle right here is 30 degrees. What I'm going to do, I'm going to start with just telling you what you need to know for physics problems. What you need to know for forces on a ramp, specifically, is the angle of the ramp is equal to the angle between mgy and mg. So this angle is 30 degrees. The angle between mgy and mg is 30 degrees. Now you can start by just memorizing that. And I recommend that most of you just memorize this rule. The angle of the ramp is equal to the angle between mg and mgy. Memorize it, use it every time we have a ramp problem. For those of you that are really curious about where does that come from, for those of you that don't appreciate a teacher just waves their magic wand and says, poof, this angle is 30 degrees, I want to show you quickly where that comes from. It comes straight from geometry. I'm sorry, I guess your geometry teacher probably would be disappointed with me. I'm not going to do a formal proof. In fact, I don't even have the names of all of the theorems or postulates that I'm using, but I think I can still make a pretty convincing argument that that angle has to be the same as that angle. So what I'm going to do is I came off to the side here with the green marker, and I'm going to redraw parts of this. So I redrew the ramp, and I said the ramp is 30 degrees. And I'm going to redraw mg going straight down. And I'm going to extend mg a little. So what I've done, if I can take another color here, is I've created a right triangle. And so if this is 30 degrees, we know this is a right angle. That means this has to be 60 degrees. Now I'm going to also redraw mgy. So if mg is perfectly vertical, mgy is going to be parallel to my crooked y-axis. And what I'd like you to see here is that if this angle right here is 60 degrees, then this angle has to be 30 degrees. Because those have to be complementary, and that's 60 because that's 30, so those two angles have to be complementary. And so I think you can see that whatever angle you put in as the angle of the ramp, you get the exact same angle between mg and mgy. Again, that's just a quick geometry proof. We won't be using that geometry in physics other than knowing this rule. So I'm okay, to be perfectly honest, if you memorize this rule. I'm also okay if you want to learn the geometry and understand where that comes from. All right, at this point, if we've drawn our triangle properly, we're in really good shape. We have our hypotenuse, in this case that's 490 newtons. We have the angle between mg and mgy using our geometry rule. That's 30 degrees. It's the same exact angle as the angle of the ramp. And so we can use that to solve for mgy and mgx. I'm going to say that mgy is my adjacent side because it's touching my angle. So I'm going to use cosine. Cosine of theta is mgy over mg. Again, that's my adjacent over my hypotenuse. And now I'm going to plug in some numbers this time to make this a little easier. So I have cosine of 30 degrees is equal to mgy over 490. Let's get a value for cosine of 30. The cosine of 30 is 0.86 0.66. So that's going to be equal to mgy over 490. And then we just have to multiply. So we should get here that mgy is equal to 424.34 newtons. So we solve for mgy. We're going to go through a very similar process to solve for mgx. But mgx, looking at our triangle, is our opposite side. So I'm going to put a little O over here just to remind us. Because mgx is the opposite side, I'm going to use sine. So we know that sine of theta is equal to mgx, that's my opposite, over mg, that's my hypotenuse. I'm going to plug in some numbers, and I need the sine of 30 degrees, which I believe is 0.5. And then multiplying 0.5 times 490, we should get that 245 newtons is equal to mgx. All right, so you might say, well, we're done. Technically, you're right. We did solve for mgy and mgx. I wanted to take one more minute here and show you what I think is going to be the most important part when trying to solve problems on a ramp. So you see, I made a bunch of space on the board here. I got rid of my trig. I got rid of my geometry rule. I did write the values up here just so we have them, although to be honest, I don't even think we need those. The last step to me, the most important step to solving ramp problems, is to redraw the free body diagram. Now, in this particular case, it might seem a little bit silly or a little bit counterintuitive. It might feel a little like you're wasting your time. You are not wasting your time by redrawing the free body diagram. And what we're going to do is we're going to draw it almost the way it is over there. All of the forces that we didn't touch, we're going to redraw exactly as they are. In this case, that's only normal force. In the future, you might have applied force, you might have friction force, and so you'd redraw those too. And at this point, you haven't split those up into components. So you'd redraw them exactly as they were in your original free body diagram. But that diagram's a mess, and there's a triangle in it because we ripped mg apart into its components, mgx and mgy. So what I'm going to do is I'm not going to draw mg on this diagram. I'm going to draw mgx. Again, starting near the center of the object, going down the ramp, and I'm going to draw mgy. Parallel to my y-axis and parallel to the normal force, perpendicular to the ramp. And now I feel like this diagram gives us a ton of information. We know what mgx is, so even when problems get more complex, we can use this diagram with mgx drawn parallel to the ramp to help us find our sum of the forces, our sigma f. It also, I think, clearly shows you, even though it's not a proof, even though we haven't proven it, it looks like Fn and mgy are now equal but opposite forces, and they are. That's an extra little note you can make. And I think you can tell that that's the case here because we redrew the free body diagram. So I think this last step is extra important helping you solve problems. If you can get to this step here, problems kind of turn into what they were in the past. Drawing the free body diagram. I know that took a lot of time. Canceling out equal but opposite forces. Finding the net force using help minus hinder. Solving using algebra after you plug in MA for the net force. So you can use your same problem solving process once you get to this step. And this step only has value once you've found mgy and mgx.